Hi, everyone. At the end of 6.3, I was talking about level curves in a contour map for heights of a mountain. The idea is that if you lift this level curve up by 3,000 feet, if you lift this level curve up by 4,000 feet, and so forth, the idea is that you construct the mountain, right? Where z, the height of the mountain, is given as a function of x, the longitude, and y, the latitude. Z is a function of x and y. That's Calc 3. All right, let's go to 6.4, vectors and dot products. How do we multiply vectors? There are several ways to do it. The two most common ways is the dot product, which we're going to talk about here in 6.4. And you got to make these dots nice and big, so it's not like a wimpy 3 times 4 kind of dot from arithmetic. A nice big dot for the dot product or Euclidean inner product. And there's also the cross product, which we're going to see in chapter 8. Okay, that's like a big X there. So yes, the notations aren't very creative. It's like you're making them bigger. Okay, the cross product is also called the vector product. We'll see that in chapter 8 when we do determinants. Okay, dot products, the subject of section 6.4. This is one way to multiply vectors. So let's say you have two vectors in Cartesian component form. It's very common in a Math 200 level class to say, let the vector v be angle brackets, v sub 1 comma v sub 2, where these are real scalars, real numbers. And the vector w is angle brackets w sub 1 comma w sub 2, where these are in the reals, and they're scalars. Then the dot product of these two vectors, in fact, in either order, we'll see that. The dot product v dot w, it's a nice big dot there, right? Not like your wimpy 3 times 4 kind of dot. Okay, got to make it bigger, make it clear it's a dot product between these two vectors. Because we don't take dot products between a scalar and a vector. We take a dot product between a vector and a vector. V dot w, it's going to be this number times this number plus this number times this number. It's kind of the product of the x's plus the product of the y's. It's this product plus this product. And there are different ways of writing this. You add the products of corresponding components. And notice, when you take the dot product of two vectors, they're really the only things we take the dot product of. And these are vectors in the plane. Okay, these each have two components. You better have the same number of components. In Math 252, you have to worry about that. But here, we're assuming that we're dealing with vectors in the plane. Each vector has two components here, right? When you take the dot product of these two vectors, notice that here, is this a vector or a scalar? Number times number plus number times number. Notice that the value of a dot product is a scalar. The dot product between two vectors is a scalar. So you could write it like this. A vector, big dot, vector gives you a scalar. Remember that. Assuming these are compatible, and they will be compatible in our class. These will be vectors in the plane, not 3 space. Although you could take the dot product between two vectors in 3 space, but they have to be compatible. Okay, so for example, how do we take the dot product of 7 comma 3 and 2 comma negative 4? Well, it's 7 times 2 plus 3 times negative 4. In fact, when I work out dot products, I find it easier to do the products in my head and write them down, and then perform the addition, or in this case, ultimately, the subtraction. Because personally, I often miswrite things when I try to write down a product as 7 times 2. But either way, if you help yourself by writing this all out, that's fine. If you're like me and you're worried about miswriting things, you might want to do products in your head. In any case, 7 times 2 is 14. All right. 3 times negative 4 is negative 12. 14 plus negative 12, that's 14 minus 12. The dot product is the scalar 2. That's a scalar, not a vector. Again, the dot product between two compatible vectors is a scalar, not a vector. Again, one of the hardest kinds of problems you get on a vector test is, here's an expression with scalars and vectors in it. is the end result going to be a scalar, a vector, or neither, like it's undefined? And these are hard for students. All right, what are some properties of the dot product? And why do we call it a product? In what sense is it a product? What are some similarities between this guy and, say, 3 times 4? Products between real numbers and standard multiplication. All right, so, and of course, don't worry about the numbering. Property number 1, the dot product, like the regular product for real numbers, is commutative, meaning that the order doesn't matter. V dot W is equal to W dot V, which makes sense. And in a proof, you actually show this with symbols in a Math 200 level class, but you basically show that if you switch the V1 and the W1, if you switch the V2 and the W2, it doesn't matter. So basically, the commutativity of the dot product relies on the commutativity of standard multiplication for real numbers. And again, these proofs are straightforward in a Math 200 level class. So that's one way that this is similar to an old school product. Now, I didn't list property number 2. Property number 2 is basically a zero product property. So here's property number 2. Property number 2 is the fact that the zero vector, remember that the zero vector here is 0, 0. We represent it with a point, right? The zero vector, see that notation? The zero vector dot any vector in the plane is going to give us, well, 0 times a number plus 0 times a number. You're going to get 0. The scalar 0. I'll keep bringing this down. The scalar 0. So the zero vector dot producted with any vector in the plane in either order, you can switch these by commutativity, the result is going to be the scalar 0 with no half arrowhead on top. See, that's why it's confusing. A vector dot a vector is a scalar. Okay, in the same way that in classic multiplication, the scalar 0 times any real number, like 2, gets you 0 back. Also, just like old school, the dot product distributes over vector addition. Okay, you may remember that in old school algebra, the number a times the sum b plus c, okay, we can write this as a times b plus a times c. Old school, multiplication distributed over addition. Similarly, the vector a dot producted with the vector b plus c. Remember, a vector plus a vector is a vector, assuming these are vectors in the plane. That will go without saying in our class. The result can be obtained by doing a dot b plus a dot c. The dot product distributes over vector addition. And again, whether you work it out this way or this way, you're going to get the same result, which is a scalar, because ultimately we're dealing with a dot product, or in this case, a sum of dot products. So the end result will be a scalar, the same real number for both sides. Okay. Property 4. Now, the closest property we have in old school algebra is the fact that a times a, old school, was just a squared. All right. Now, with vectors, the vector v dot producted with itself. Now, we can't use the notation v squared because it's not clear what the nature of the squaring is. Because a square means you're doing v times v. But what kind of product are you talking about? Here, it's clear that we're talking about a dot product. We never say v squared when v is a vector because you're not being clear what the nature of the product is. Is it a dot product, a cross product? What is it? So we never say v squared when v is a vector. All right. V dot v, it turns out it's going to be the square of the length or magnitude of v. Okay. And by the way, this is a scalar, right? The dot product of two vectors is a scalar. This is, again, a scalar. Okay. You can think of it in terms of the Pythagorean theorem, maybe, right? Imagine an isosceles triangle, an isosceles right triangle, right? It's kind of like the idea. there, kind of like the idea. Um, okay, so v dot v equals the magnitude of v squared. So the idea here, in terms of computation, so you have angle vector v1, v2, okay, dot product it with v1 dot v2. Okay, v1 times v1 is v1 squared plus v2 plus v2 is v2 squared. And that's how I related it to the right triangle. In case you were wondering what I was doing, I was relating that to a right triangle where I was saying, okay, if this is v1, this is sorry, if this is v1, if this is v2, the vector v1 comma v2 is this vector here, the vector v. So v1 squared plus v2 squared, the sum of the squares of the legs, that gives us the square of the hypotenuse, the square of the length of v. So if you want to think of this as a length, we're talking about the length of v, the magnitude, or r. Okay, both of these sides will equal the square of the hypotenuse. All right. Next up, we're going to talk about a key application of dot products, finding the angle between two vectors. Next time.